fine.
I'm just saying, okay, so you saw what I posted.
What?
Oh, yeah, Japanese.
Oh.
Those are the unofficially.
Your diagram doesn't work, does it?
Oh,
why?
I've never done
I'm
it.
done.
Okay, then I'm done.
Because they write, I believe the
But
reverse
my, did my Floyd work or
a
no?
lot of stuff and it will.
There's
I got the point.
some which is great because the Japanese stuff is always.
Okay, well, I'm telling you, that's the problem.
Also
Yeah, but I think
That's what we use.
A lot of times they're doing way more.
The exact same, if you.
A lot
This
of
is wrong with my
this,
everything, so I gotta figure that out.
so this is the
Because
same
you're doing way
diameter
more than you need to because you just went copy to piece for piece instead of thinking about what he's already provided.
This part,
Literally
the silk
1,
wrap
2,
pen, if
3,
you push it
4,
in
5,
further,
6 lines. Voice
it's
algorithm
useful
is
for
6
doing
lines.
small light
This whole
bulbs on
assignment.
indicating lights.
How many do you have?
Really?
Yes.
I could see that.
I have 5.
How long are you gonna need? Okay, you said nuclear baby, what does that mean?
Nuclear reactor.
I feel like lots of.
Like submarine?
Aircraft carriers, yeah.
Were you on a submarine? You're too tall, bud. I was like, a submarine's gotta kill you. Submarine sounds terrible.
You're running, you're still running assignment 3, not PY.
But you also knock your head on something on a surface.
Yeah.
You don't like ships at all, though?
Oh, no, I'm actually using on purpose.
Oh, that's interesting. So you were very. It's fun, but I feel like I'm gonna break it if I look at it. It's like, you know, it's like a paintbrush.
But not
So it's like, so that.
Running.
Yeah, Pentel makes an 0.2.
Today, I wasn't.
Yeah, most
Like, I spent
7 is much bigger.
so.
Right, yeah, you're right. I'm dedicated to this.
What I do.
That's okay. I was saying dumb shit all
I
the
feel like
time.
maybe
That was that
it's
auto
not
dispenser.
like
I didn't think they'll make-
Like a shaker.
Oh,
Yeah.
you just put pressure on
Doesn't
it.
count towards project.
Let it sit cool.
Oh,
Although.
Yeah, I feel like
I've seen some where you shake it and you let it.
It's called Pentel?
See the something, like, maybe I raised this law.
See, but I.
I mean, not like it's cheap as a baker.
You can, you
During
can buy
my
Leaning
Fountain pen?
2000.
I was like, during our break.
You can buy Leaning 2000 on Amazon.
So I like, stood up to go back
Stick with bunny.
inside.
$200.
When's the one stolen?
One small install.
Okay, I forgot.
Are you staying after class?
Yeah.
I'm not
like.
But like, I think. it's like-
You staying after class, we're gonna set-
Really super, like, a lot of that.
It's not like.
Exactly, but like, I was really going to the library.
Can't work with you.
But it is a question.
So the place.
It is true. I do my best to work away from all of you. Sorry that happens. I don't
God, I run it.
In your,
This is normal for
in your
everybody.
key den.
Yeah, my key did, yes.
Did you guys hear what happened to Mohammed Sheikh? Had a burning his home. He's in the hospital, so. I don't have more details. It's your colleague, so I thought you guys would like to know about it.
What happened?
I think he burned, had a accident with fire. He got severe burns in the hospital.
Okay.
You guys,
His best wishes, yeah.
you know him? Right. So, they're trying to see if there is an easy way to contribute to some fund. I know that MSU Denver has the student emergency fund. Definitely this fund can be used in situations like that. But the department is trying to find a way to share a link where anybody can contribute to this fund. So I'll keep you guys posted if I hear more information about it. Okay. Do your best. I know that we did talk about the shift reduce algorithm, but I mean, we didn't have time to look at the implementation, so maybe some details about specifically about the algorithm, perhaps you guys don't remember, but let's use this to the quiz to help you retrieve that information. Okay, so just do your best. Don't worry if you don't get it right. You guys that are online, you're welcome to participate too. So doing the bottom-up parser using the shift reduce algorithm, and just remember the shift is the procedure that actually will consume a symbol and the corresponding token value. It's going to be consumed from the input, and that's the moment when a new tree, right, that potentially will be connected to an upper node. So it will be a branch for another node, and we'll change the state. Remember that this shift reduce algorithm is a state-based machine implementation, and that's also the shift operation. The parser will change its state. Remember when you had like S2, S is for shift, 2 is for the new state that the machine will move to. And those symbols that are read from the input, they will be added in the parser stack, which is used to control the symbols that are being read and they're still not connected to an upper node. You guys remember the reduce operation? For example, reduce X. In the shift operation, shift X, X is the state, right? Reduce X, what is that? Do you remember what X means? Finger. Right. So it means use, so X refers to the production to be used to replace one or more symbols, tokens from the parser stack. They will be condensed, put in a, will be connected, right, to an upper node. So collapse one or more branches over a single parent. The last one, I had these questions. I don't expect you to get it right, just your best shot. Just remember that there are 3 symbols here. So this is one token. This is, you want to apply this production here, right? You want to do a reduce operation, right? You have F going to, this is what you have in the stack, but remember, does the stack only contains, according to our implementation, does the stack only contain symbols, or does it also contain symbols and state values? Can't read it. You good? Away a little bit? Okay, got it. Okay. So it's actually 6 because each, when you read, you're going to use the stack for 2 purposes, to store the token values and also the state values. So you're going to have 2 for each symbol. So if you want to do 3, you want to remove 3 symbols from the stack, you actually have to double the pops, because for each symbol you have a state. That's why it's 6. Is there a systematic way to generate the SLR table? That's it, right? You might get a carnival in this.
Anybody put C?
Oh, only one got it wrong. I'm not gonna tell the person's name, but I know you. You probably made a mistake.
No
Ooh.
carnival.
Why? Somebody's working against us here.
User error.
I think it was Bob.
User error.
Someone is working against us.
This is sabotage.
He's trying to move the suspicion away from him. It wasn't Bob. Okay, so yes, you can use the tool that we use online. Let's use that. So you have one that you have to write a function procedure for each production, and you have this other one that uses a external table and kind of as an input for the program. So which one do you think in general will use less lines of code?
In general or potentially? These are like 2 different.
Potentially, right? Okay. Because it really depends on the size of the grammar.
Yeah.
But which one has more potential to generate a code that is more compact, or it wouldn't be affected by the grammar? One is highly affected by the grammar, right? Okay, so the SLR bottom-up parser is not affected by the grammar size, because one of the inputs for the algorithm is the table, right? And the table is not code. It's something that is external to the program. The program is always going to be the same. On the other hand, the top-down parser you have to write, right, a function or procedure for each production. So if you have a super large grammar, you're gonna have to write a lot of functions, procedures, right? Okay.
So I have a question.
Yeah.
Most languages aren't as simple as, you know, the one that we're using, mouse. So in general, why would not regular, but like, why would normal languages that have way more stuff going on, why would they ever use like a top-down parser if it's just more code to write?
Well, if you're talking about you're actually gonna write your own programming language, you're highly encouraged to generate the parser using a tool. So the fact that the code will have more or less lines of code, it really doesn't matter if you use a tool, right? So we're looking at the actual implementation because this is a programming language course, right? We want to learn a little bit more behind the scenes of those compilers. Speaking about behind the scenes, let's take a look at the actual implementation for the SLR parser, and then we're gonna move on. But we need to finish activity 8. So let's open activity 8.
Activity 9, is that?
I think so. Is it 9? You're right. So activity 9. Get myself organized. So grammar, and these are the two inputs for the parser: grammar and SLR table CSV. First, let's get the grammar. Okay, so I'm just gonna copy this grammar here. Get rid of these spaces. By the way, if you want to use this code for programming assignments, feel free to use it. Of course, you have to. Basically, the programming assignment will become working with the tool that generates the SLR table, and make sure you use the correct formats, but basically you don't have to code anything. So it's an option you guys should consider. So I have the grammar here. And what I'm going to do is, you see that there is a grammar class here. So let's just, so this grammar opens the grammar text file, and it has these methods here. Get LHS. So that's the method that allows us to get the left-hand side of a production. Pass an integer, that's the index, the production index you want. And there's also the get RAHX, which gets the right-hand side of the production, returns an array. Let's see if this actually works. We can test that using, let's maybe use syntax analyzer. You see, this is how you instantiate the grammar, passing the grammar's file name. Let's try that. We can also go to grammar and create a companion object. Say object grammar, then use main. Let's just instantiate a grammar. Grammar file name, let's just, the name of the file is grammar.txt. Let's just print grammar. See what happens. Okay, so it was able to parse the grammar, showing the grammar here. For example, if you're interested in getting this production, and do grammar dot, let's get the left-hand side of production index 2. Let's see what this will gives us. It should give expression, right? Let's see what happens. Okay, we got expression. And if we try the right-hand side of production 2, we get, what is an expression? That's not an expression. I think we need to call this method here, make string. Let's try again. There you go, expression dash term, or minus term, right? Okay, so this grammar class is basically allows you to read a grammar and be able to query the grammar for left or right hand side of a production. So now let's move on to the SLR table. You see it's empty. Go to the documentation. So you're gonna get this grammar, go to the tool will give you this, and you need to come up with this format. Basically, you can just, the best way to do that, if your intention is to use an SLR grammar for the assignment, is to, in my opinion, you just select and copy and then paste it in Excel or any other spreadsheet. Then you have to do some substitution because like, for example, how are you going to identify the tokens, right? Are you going to use numbers? It's best to use numbers, the token value, than the actual symbol for the tokens, right? So instead of, this is what you're going to have initially, I would recommend you to replace those tokens by the token values. So replace the terminal symbols with their token values. This is already in the format that we need for the SLR table. So I'm just going to copy this. This is what is already formatted in the format that the tool requires. You still have to deal with these extra spaces or new lines, just get rid of them, and you're going to have your SLR table ready to use with the algorithm. Okay, save it. And as also we had the grammar class, we also have the SLR table class. This SLR table class allows you to parse that SLR table and has methods for you to query this table, like get action and get go to. So let's create a companion object just to test and get to know a little bit more about this SLR table class. So I'm going to create a companion object just like we did for grammar. I'm going to do for SLR table. I'm going to create a main so we can do some testing. Okay, so let's see, how do we instantiate an SLR table? Here's a line that shows how to do that. As the file that contains the table. So the file is named SLR underscore table CSV. So this is what I'm going to do. SLR table CSV. And let's just print it. Didn't like index 13 out of bounds. Maybe we need a new entry here. Something else. Sometimes when you copy and paste from Word, you get some weird characters. Those are the worst arrows to This looks like a comma, right? Don't even recognize it. So let me grab the table before I copy and paste to Word. Sometimes that's the problem. It solves the problem. Let me see if that works. Okay, I got it to work. Let's compare. Here I have 16 lines. Here I have also 16 lines. So I don't know what's the difference. I'm gonna take too much time figuring it out. I'm just gonna replace this one with the one that is working. But in my opinion, they look the same, but close. Okay, and I can provide you the link for the actual file, but it looks the same to me. Okay, so as you can see, the Slr table object has all the actions and all the go-tos. So first it lists the actions, and then the go-tos. And you can easily query for a specific action. For example, I want to know, for example, this one here. Let's use this one here. State 2. So here it's 1, 2, 3. Let's use, it looks like 5 or 6. 1, 2, 3. I think it's 4. So let's use 2, 4. 2, state 2, token 4. It should go to, the action should be shift 10. So let's see if it actually gives us that. So get action. So I need to pass the state. The state we want is state 2. And the token value, let's say, did I say 4 or 5? 4, right? So let's see what action this will give us. That's 10, okay? So as you can see, the Slr table object allows us to query for a specific action or a specific go-to. So this is ready to use. Now let's go to the syntax analyzer and see what needs to be changed. Okay, so the first thing here is it gets the action. The parser always knows its state. It starts at state 0, and it will read the token from the scanner, from the lexical analyzer. We'll get the token, and we'll use the state, the current state, and the token ID to figure out what is the action. We'll print the action. Right? If the action is undefined, it means that you got a syntax error. So you should just throw an exception, right? So let's do that. Let's throw an exception when the action is undefined. You can just say syntax analyzer error. So what I'm going to do here is if the length of the action is actually a string. So if the length is 0, there's nothing there. So we're just going to throw new exception. Just going to say syntax.
Where do we can get Tina's name?
Syntax analyzer error. Okay. So this to do was really easy. Now we know that the action is a shift operation. Update the parser stack. So we need to append two things in the parser stack. First, the token, and then if it's, for example, shift 3, the new state is 3. So we need to update 3, the value 3, because that's the state value that should be updated in the stack. So let's do that. So stack is the stack that we're using here. And append token. Okay. And just gonna make it as a string. The other thing we need to append in the stack, into the stack, is the action substring 1. Because, for example, if S is the action is S3, substring 0 is the action. Substring 1 is this value here. That's the value we want to push into the stack, which is the new state, right? That's what we're doing. So basically, this is what we need to do for to update the parser stack. Create a new tree with the lexeme. You guys know how to do that. I'm going to call it tree. New tree. Lexeme get label. So I opened this, I almost got drunk. Can you smell the alcohol? Pure whiskey. So get label, we're going to push that. We're going to not push. We're going to create a node with the lexeme's label. That's what we did here. Push the new tree onto the stacks of trees. So remember, every time you read a symbol, let's say I'm reading an identifier, we're going to create a new node with the identifier, right? And eventually, I'm going to have many nodes. At some point, I will connect these nodes, and this is probably what? An expression, right? Something that is a variable that I'm going to use a production in reverse to condense these tokens into a upper variable. Well, this tree of nodes, it's called trees. So we just need to do, it's just a list of tree nodes. So we're just going to do trees and tree. This is how we're going to add a new tree to this list of 3. And then acknowledge reading the input is just moving forward the lexeme. Okay. So that's it for the shift. So shift was reasonable, right? You just read the input, push 2 symbols into the stack. The first symbol is the token value that you read from the input. the second symbol is the new state of the parser. After that, you create a node with the tokens label, and you add that tree node into a list of trees. What is more complicated is the reduction. So the reduction tells which production to use. So first step is to get the production to use. We're gonna use this. The index, right? So if I say R5, that's the reduction. 5 is the index that tells which production to use. So let's get that value. It's the substring 1, right? We're going to convert that to an int. That's the production to use. Let's call left-hand side grammar get left-hand side using index. Let's get the right-hand side of the production to use using grammar get right-hand side index. Okay, so this is how we get the production to use based on this reduction operation. Update the parser stack. So we need to do the pops. It's all about how many pops you're going to do. It's all about the size of the right-hand side of the production. If the right-hand side of the production is something like E goes to E plus term. So we have 3 things here that we want to condense. Because for each symbol, we have onto the stack the symbol plus the state. We have to pop 6 times, right? Because each symbol, you also need to pop the state. So let's pop 6. Well, depending on the length of the right-hand side, we need to figure out how many pops we're going to do. Scala has some very interesting methods that we can use to operate stack. There is this one called drop right in place. This is very useful for what we need to do. In place means that the method will actually modify the stack. So we don't have to, it will not create a copy of the stack, modify in place. Drop right, we have a list of, so the stack from left to right, the top of the stack is on the right. So if you want to pop many, you can use this drop in place. As you notice, this stack is not actually a stack, it's a list. So we're using drop methods to simulate pops, okay? We're gonna get the length of the right-hand side of the production, and we're gonna multiply that by 2. So so if the length is 3, we're gonna drop 6 symbols from the stack. The new state that we're gonna use to figure out after we pop these symbols from the stack, what's going to be on top of the stack is going to be a number that represents a state that we're going to use to figure out the next state to go. I don't know if you remember that part of the SLR algorithm, but this is how you consult or you search this go-to side of the table. You look at the state that is on the stack and the left-hand side of the production. For example, if on the stack it's saying state 6 and the left-hand side of the production or the reduction is expression, it means you have to move to state 11. So this is what we're trying to figure out, what's on the stack at this point. So stack last. That's on what's on top of the stack. We're gonna use strip just to remove any spaces that we have there. And then we're gonna convert this to an int. And after that, this is probably the most complicated step. We need to append the, well, let's do that in 2 steps. New state, let's call it new state. I'm gonna consult the table, get go-to. I'm gonna pass the state and the symbol. So basically we're doing the search here in this part of the table to figure out what's the new state to go. Let's call this all. And now we just need to append, update the stack. So stack and left hand side, which is the symbol that we're condensing, right? We're condensing 3 symbols that we pop from the stack into the left hand side symbol, right? And then we're gonna append the new state. I will share this code. You can use as a reference. We're almost there. Did the soft wrapping, but it's not doing it. So we need to create a new tree. The left hand side variable is its label. That's the node that will condense the other branches. Now we're going to do the condensation of all the trees from the right side of the list of trees. We're going to move those up, make them children of this new tree that we created. This is how we're going to do it. You should open the slides. This step is a bit more complicated. Get a situation here. Okay, this is the good one. Reduce 5, remember? So reduce 5 means that we need to apply, oh, we already did this. So now, reduce 3. So this is a good one because we're going to condense these 3 trees here. But look, the list of trees has actually 5, right? 5 nodes. But when we see here reduce 3, it means that we need to condense the 3 trees that are on the end of my list of trees. So only these 3. I'm not going to condense the first trees. I'm going to condense the 3 last trees. Okay, so that's how the algorithm works. So this is what this part of the code is doing. It's looping through this drop. It's not drop in place. So it will just drop all of the trees, a copy of that list of trees, right? We're using drop, not drop in place, of all the trees that are on the left side, right? So for example, tree's length is 5, right? Because we have 1, 2, 3, 4, 5 trees. We're gonna drop tree lengths 5 minus right-hand side length. Right-hand side length is 3. So 5 minus 3 is 2. We're gonna drop these 2 here. What is left? The trees that we need to collapse. This is, and at each iteration, we're gonna add this tree first as a branch of the new tree that we're creating with the symbol T. Basically, this is what this procedure is doing. And now we're actually going to drop these. So these trees were collapsed, right? We need now to drop the trees, those 3 nodes here, and add this one here. So at the end, we're going to have only 3 trees. Trees. Drop right in place. Then append the new tree to the list of trees. That's easy. Trees. And that's it. So I probably you guys are thinking that that's kind of complex, but okay, I give you this. The algorithm is more complex, but you just need to implement it once, right? Because you just need now to give any Slr table that is correct that you can easily generate. The algorithm should work. Let's actually see if it works, right? So we're trying this one here first. There we go. Okay, so start expression minus term, right? Expression. All of this is expression minus term. Term is a factor label 8. That's the second part here. Then you have an expression is expression plus term. And this first expression is just 52. And the other one is term divided by term. And the first term is a multiplication of 2 terms, x and 231. So that's correct. So let's try another one. Source 2. Okay, so also this for second. Z99 plus multiplication here, right? Oh, we have the parentheses. You see the parentheses here. Closing parentheses. So it's basically saying that a factor can be an expression in parentheses. That's exactly what is seen here. A factor is an expression inside parentheses. Okay, so this is, you guys, as I said, feel free to use or share this code. You can use in your programming assignment. If you don't want to spend time actually writing the top-down parser, because you have a lot to write, and the algorithm is much simpler, the algorithm that we discussed. But on the other hand, there's a lot of code that you need to write. This version here, you don't have a lot of code. Actually, zero code, right? Because I'm going to be sharing the code. You can evaluate the code. But you have to generate these two inputs in order for the algorithm to work. One is the grammar, this format, and the other is the table. The table is all the logic is embedded in that state machine, right? And you can generate that state machine, but you need to make sure it's in the correct format in order to work. Other than that, you need to make sure that the parse tree that is being generated by the program is in the exact format for the mouse assignment. Because the mouse interpreter can only run the code, the mouse code, interpret the mouse code, if the parse tree is correct. Is in the exact format that it expects. Okay, so you can work with a partner for the programming assignment. Talk to your partner if you're working with someone else, and decide whether which route you want to go. Right? If you want to do the top-down parser or the bottom-up parser. I see pros and cons on each of them, right? So you need to talk and decide. Okay. Any questions about the programming assignment? Have any concerns? Anything you want to ask? Yeah.
I pulled down the copy and it seems to come with, what is it, source 12, which has less than in there. But so far our grammar does not include less than or greater. Should we add that or?
So source 12 is not shared?
Oh no, it's shared. It's just it has less or greater characters in there. And it's not in your interpreter.
No, that's just to check the lexical.
Oh, okay.
Okay, so it's in purpose.
All right. That's it.
Yeah.
So, quick output question. So when we're parsing our syntax and producing our tree, I have my tokens in value label, not label value. Does that matter? It's just swapped in your example. I can show you. But
Yeah, you can, because I believe it's a dictionary, right? If it's a dictionary, I don't remember.
Okay.
It shouldn't matter.
Okay, because when you make a new tree, you
pass the label.
Yeah, you give it the label.
Yeah.
Then when you modify the attribute, you give it a value, and I think it puts that first. I mean, it gives the right output, but it's not in the right order.
You can try the mouse interpreter and see if you can run the code.
Okay.
Try that. Yeah.
Still works.
You did that?
Yeah,
Okay.
it just prints the value attribute before the
Yeah.
label
Yeah.
attribute.
I just
So
wasn't
the
sure if that was-
output's different compared to.
I think what's important is the name of the attributes, but the order doesn't.
And the names are correct. It's just
Okay. So it should work.
Okay,
You should
awesome.
try. Any other questions? Nice. Okay. So we're starting a new topic now. Some of you might be feeling relieved, right? New topic, yay. We're going to start moving up. We started doing the lexicon analyzer, the syntax analyzer. Let's discuss a little bit about semantics. Initially, when I was planning this course, I wanted to do all the phases, including the semantics. But the problem is there isn't much standard on when it comes to semantics, definition, rules, or expressing semantic rules for programming languages. So the theory is much more standardized and established for of course, the lexical part and the syntax when you define grammars, right? But for semantics, there isn't a standard like EBNF, for example. So that creates more challenge. But let's at least discuss some of the aspects related to semantics. And this is gonna, today, discussion will be very light after the heavy stuff we had in the beginning. So first of all, we need to talk about, in order to talk about semantics, we need to discuss things mostly related to variables and identifiers. Most of the semantic rules that we're going to discuss later, they involve rules related to variables. If the variable is defined or not, if the variable is visible. So we need to talk about variables naming, also binding of variables, which talks about how the variable attributes are associated with specific values, and scoping of variables. Okay, so let's talk about those things, starting with names. So as you're already familiar with, names are important when you write code, because this is how you will identify entities in your program. Those entities may be a variable, may be a function. So you have to give names, right? Name of a class or other constructs in your program. So for most programming language, you're gonna use letters followed by letters, digits, underscore. There's always, you have to look at the specific language that you're using to learn the rules for naming identifiers, right? This is basically the rule used for Java, for example. Another thing you have to look, take a closer look, is whether the programming language is case sensitive or not. Most programming languages are case sensitive, but there are some exceptions. For example, SQL is not case sensitive. Okay, so other languages like Fortran, Pascal, those are other examples of case sensitive programming languages. Most basic dialects are case sensitive, but those are exceptions. Special cases. Sometimes programming language, they use some special symbols for variables, or prefixing the name of a variable to have different semantics. For example, PHP. You guys know PHP? Right, so mostly if you're into web development, it's very big in the web development, software development. It requires variable names to begin with $. Okay, so variables in PHP, they have to begin with $. So PHP is actually a recursive acronym. Right? So it's you guys know what PHP means? It's PHP. It's PHP hyper processor. So the name has PHP on itself. It's just a joke that they wanted to make it a recursive acronym. Other languages like Perl, have you ever heard of Perl? Actually, Python was highly influenced by Perl. They also use special characters at the beginning of a variable name to specify its type. For example, if scalar values like numbers, for example, single value variables, they use the $. But if it's a collection like an array, it uses the @ symbol and % for hashes. What do you guys think about these conventions? Do you guys think it's useful or not? Create confusion? Did you have any saying on that? Yeah, right.
I like the Ruby's instance and class variables. The @ symbol really sticks out at you. But you don't have to look for a word, it's just a single character.
Yeah, so these kind of help for readability, right? You kind of associate. It starts with an @ it's an array, it's a collection, right? Any other comments?
Probably a little bit easier for the lexical analyzer.
Yeah, that too, right? Say that too. But those things are mainly put in the programming language in order to improve readability. Here is an example. This is a code in Perl. So as you can see, numbers is an array. And you're using this symbol, the $_. This is interesting because it's called it's a default variable and it's automatically assigned depending on the context. That's pretty cool because what you're doing here when you say for each at numbers, basically it's implicit that you're trying to get one individual element of that array, right? But you don't see where those individual values will be stored within the loop, right? So that's when an implicit variable comes in place in Perl. So it's implicit because you don't explicitly assign a variable. The Perl will automatically assign to that implicit variable, which is the $_. I think that's pretty cool. Well, there are some limitations, right? If you have two nested loops, right? So the implicit variable probably will only work for the inner loop, right? The outer loop, you have to do something explicit. Now you're talking about Ruby. Global variables begin with $. Instance variables, you use the @, so different. And class variables, those are static variables using two @. That's kind of weird, right? Double @ in here. But this is a person written class in Ruby. So as you can see, name is the parameter for this initialize. And because I created on the left-hand side of this assignment @name, so this name here is an instance variable, right? Unfortunately, the example doesn't have class variable. Here it is, a code in Ruby. I never used Ruby, it's just an example I found. Okay, so moving on to special words, words that are part of a programming language, vocabulary like if, else, while. So let's make a distinction between what is a reserved word, what is a keyword. So basically a reserved word, you cannot use or you're not allowed to redefine it. keywords, they can be redefined. Okay. Most programming languages will define reserved words instead of keywords. But there are some exceptions that you have to be aware of if you're using a new programming language. COBOL, for example, had a particular large number of reserved words. Look at this. Fortran didn't have reserved words. So technically, you would be able to write something like this. If, and this if here is a variable, that's horrible, right? Then, this then is another variable or something that, or a function call or something, else. So you can do that in Fortran. Maybe this should be in a t-shirt, right? C++, final and override, they're not listed as reserved words, so you can redefine. So if it's not a reserved word, you can redefine. So here I'm redefining final and override, and I cannot use final and override as special words anymore because I redefine it as variable names. Okay, so whatever I said here about names, it usually applies for variables and other constructs that requires identifiers, such as naming a function, naming a class, right? But let's focus more on variables. As you know, variables are abstractions of computer memory cells or collection of cells, if it's an array or something. Data structure represent a collection of things. Allow programs to address memory using names, we know that. And a variable, I'm looking specifically from the point of view of programming languages, we associate to variables. One of the most important things when you're designing or studying a programming language is the attributes associated with variables. We already talked about names, but also the address and its value. Those are usually called L value and R value, because usually what you have is that in an assignment, you have the left side of an assignment is the address, right? Where you're going to store. The right hand of the assignment, the R value, is the value that you're assigning. So those, you may see text referring to L value as the memory, the address of a variable, and the R value as the actual value currently assigned to the variable. Then you have variables type, its lifetime, and variable scope. So the type refers to the range of possible values that can be stored, and the set of operations that you can perform with your variable. Here's just the types associated available. Those are the primitive types of Java. Have some operations that only work with numbers. Concatenation, for example, only will work with char and string values. Variables, Boolean, you can put that in using logical operators, right? Relational operators you may be able to use. You will be able to use with numerical values for comparison. So all those things you should know. So let's talk about variables declaration, right? So as you know, you may have a programming language, you may be using a programming language that require you to declare a variable before you use it, or some programming language do not require explicit variable declaration. But just make, let's be clear that a variable, there's no such a thing as variable that is undeclared. What you have is explicit declaration and implicit declaration, right? So the explicit declaration is when you explicitly put the variable and its type. So you're explicitly telling that this variable has this type. But other programming languages, such as Python, for example, has what we call implicit declaration. You just assign a value, and based on the value being assigned, you kind of declaring the variable in an implicit way. But this concept of declaring a variable that's when you define or you do the binding, I'm going to talk about binding, of a variable and its type, right? So most programming languages, they use explicit type declaration, but you can also have implicit type declaration. You can use implicit type declaration or variable declaration using naming conventions or type inference. Okay? Naming convention is hardly used. Okay? So you're not going to see many programming languages doing naming conventions anymore. Although we saw some examples where you can have some convention depending on the prefix used for naming the variable. So like if you use dollar as a scalar, if you use at as an array, but that's more for readability. And of course, the compiler or the interpreter will check that if what you're saying is actually what you're doing. But implicit variable declaration will most of the times fall into this case here. It's going to be based on type inference. That's what Python uses, for example. One example of a programming language that uses implicit variable type naming convention was Fortran. And I think I mentioned that Fortran, if your variable begins with letters from I to N, lowercase or uppercase, it was assumed to be integer, right? That's why we use I as the counter, and then J, K. It started with Fortran naming convention. And this is the example of Python using Python type inference. So look at that. X was assigned 10. When I printed the type of X, I got int. But in line 3, I changed and I'm assigning a new value. So the type is dynamically changed to a float. And I can do that using the same name for the variable. Okay? So this is what we call type inference. You use list, dictionary, change all the time. Good, so let's start talking about binding. Binding is this association between an attribute and an entity. That's the generic definition of what a binding is. We're most interested in those type of bindings here. So there's the type binding, storage binding, and scope binding. This is type binding, right? The type binding is dynamic here. You can see that it's dynamic. We're changing the type associated with variable X. Storage binding refers to where the variable is being stored in memory. In scope binding, it's about visibility of the variable. We're going to discuss all these things. So the binding can be static or dynamic. Any type of binding, in the context of programming language, can be static or dynamic. So static, as you know, it's fixed, right? Once you set a binding or you associate a variable with an attribute, like variable name X, I'm associated with an int, and I can't change that anymore. That's static binding. For example, Java, if you put int X, later on, within the lifetime of this variable, I can't change and say floats X. No, because the type binding is static. But Python, for example, the type binding is dynamic. I can change that within the lifetime of the variable. Does that make sense? Static and dynamic. You can also apply to storage or scope binding. So let's start with type binding. So type binding is the association of a variable with its type. There has been a significant shift to language that use dynamic type binding. So here are all the examples of language that are that use a dynamic type of binding. So Python, Ruby, JavaScript, PHP, they're all dynamic in the sense when it comes to type binding. So shouldn't I have show you this slide? But what do you think about dynamic type binding? Do you guys like dynamic type binding, or you prefer static? What do you think are the pros and cons of these type of bindings?
I think it really depends on the size of the program. Like if you're writing something that's relatively small, like maybe it's only one file, it's kind of simple, like the dynamic type binding is nice because you can just write it and go. You don't have to think about it too much.
Great for prototyping, right?
Yeah.
Experimentation. I agree with that.
Yeah, when things get big, static binding makes it easier to reason about what your program is doing, I think.
Good point, Letitia.
I think also you have to talk about the way most programming happens in corporations nowadays. It's not usually a single person who owns something. It's usually floating between teams.
You work in a team. Do you think it's best the static or the dynamic?
I think static improves readability when new people are coming to
And it makes it easier to find errors, right? Too. That's important, right? So static type binding is usually produce code that is more reliable. That's important when you work in a team, right? Right.
I feel like it's really counter variables using one single variable and constantly reassigning it. You kind of lose what it is trying to represent. Whereas if you have static typing, that won't happen.
Yeah. So and that's the big issue here is the readability, right? If you keep changing, it's the same name. Later on, you're gonna start thinking, what is this? Why am I using this variable again? Is it a string? Is it a, right? You kind of lose track, but as Harrison said, if the scope of your project is small, that's not a big issue, right? But in larger projects, that becomes a situation that it creates a problem, right? Anything else, Malcolm?
I think naming convention becomes a lot more important with those dynamic type languages, just to make sure that you don't have that problem. You want to be able to make sure that no matter what context you're using the variable in, you can still figure out what it is. Versus when you have static typing, you can always just go back to the initialization to figure out what.
Picking good names helps, right?
maybe being better with your documentation as well.
Yeah, it reduce the problem that we were talking about, right? And keep changing the uses of the variable, but if you use more names that are more meaningful, you may not have that situation, right? Yeah, I agree. Okay, so disadvantages of dynamic typing. I know that there's a big fan club of dynamic type binding. I think dynamic type binding or dynamic language regarding typing, they're more, they give the programmer, the developer, more freedom. And that relates to creativity, right? So when you have something that you want to explore, that's when I think it's a big advantage, right? I'm teaching data mining this semester and we're using Python. And I did data mining in the past using Java, and it's a big shift when you do data analysis using more dynamic language, because you want to explore what the data is trying to tell you, what sort of insights you can get from the data. So situations like that, prototyping, you don't know exactly where you want to go, right? You don't have specific goals you want to explore. I think it makes a tremendous difference using more flexible language, more dynamic, like Python, for example. But if your concern is produce a code that is more reliable, you may consider language that is more on the static side, right? Because you have a price, when you have more freedom, you also you have to be careful, make sure your code still reads well. And if the compiler can't tell what's the type associated with the name, the compiler can't check, right? So if your language provides the ability to change the type of a variable dynamically, how basically it's going to be really hard to develop a compiler, right? Because the things can be changed as you run your code. So that's why most dynamic type of language, I believe all dynamic type language, will use an interpreter instead of a compiler. So because of that, as you know, the interpreters are a bit slower compared to the code. Interpreted code will run a bit slower compared to a compiled code. So that impacts execution time. I don't know if we have an activity to do today. Let's take a look. The activity we have is about storage binding. Let's continue a little bit longer. Storage binding. Okay, so now we want to associate a variable to its location in memory. So the lifetime of a variable is the period of time, as the name suggests, where the period of time when the variable exists in memory, right? So at some point, a variable will be allocated, will be created, and at some point, the variable will be deallocated. Within its lifetime, it might be the case that at some point, the variable might not be visible. So that's scope. Okay? So this is going to be maybe a little bit of a review of OS. You guys studied that, the memory segments of a process. You guys did operating system, right? So you should be familiar with this. Maybe you know this better than me, but you have a process, a running program, and you have on the bottom usually you have the text segments where your actual code of your program is right. When you say text, it doesn't mean it's the actual source code. Okay, it's the actual binary code, instruction code that depending on your platform, right? So that's the area where your code resides. And then you have the BSS, this area is used for static and global variables. Then you have the heap, which is for dynamic memory allocation. And then you have the stack, or the call stack, used to control function calls, right? And also, it's used to maintain the state of the variables used or defined within the scope of a function. Okay, so text segments contain the instructions. We assess global variables and static variables. So this area doesn't change. And dynamic, it usually grows up, but this is just a convention, right? But one important thing to know is that the stack area, the heap area, they compete for the amount of space here that is shared among them. But just so you know, there is a limit of how much memory you have allocated to a process, although you can use specific operating system system level instructions to define more space for your process other than the standard that is provided. So the call stack, sometimes called runtime stack, you're going to use to store local variables. So those are variables defined within a function or within a scope, within a block. So we're going to talk about all the levels of scope levels that we can have. But we're talking about variables that we define mostly within functions, because every time you have a function call, a stacks, it calls segments will be created and pushed onto the call stack. So every time a function call is called, you're going to have a new stack segment pushed. And when the function resumes or returns, the stack segment is popped out. Here explains this. Every time there's a function call, it's actually called stack frame. So the stack frame is pushed, and the stack frame contains all contextual information associated with that function call, including the local variables and their current values, right? So when the function execution ends, its associated stack frame is popped out. So important here for us is that when you declare a local variable in a function, you know where those variables will be created in the stack. Of course, we don't go too deep because we don't have enough time. This is programming language, it's not compilers. So if this was just compilers course, we will be actually looking at how how are you going to define when your program loads, how are you going to define where each variable will be allocated in memory, right? So those are things that at some point the code generator needs to figure that out, right? Depending where those bindings should take place. Should the variable be created in the heap? Should be created in the stack? So all those things need to be defined, and those things will be translated as low-level instruction calls to the operating system. So of course, the code generator part of your compiler is highly dependent on the operating system, right? Because the operating system at the end is who's going to run your code, right? With your computer. So as I said, stack frames contain local variables. The on-screen is inside functions, including function parameters. Those are also local variables, and the return address. The return address is the address within this area here that tells which instruction should be executed after the function returns. This is a video that if you're not sure about how the call stack works, I recommend you to watch this video. It's actually funny. The guy explaining, you can do it to do something a little bit lighter.
Teachers, and have I got stacks to tell you about today?
Have you seen this
Stacks are
video?
a fairly advanced concept in computer science. They come up at A level, but really there are two different types of stack that you need to know about.
Can you hear?
One of them is a data structure, which we'll talk about in another video. But today I'm going to talk about the call stack. The call stack is the part of memory that keeps track of what's going on while a program is running. So let's have a look at a demo program written in Python, and there's a link to this in the description below. So this program contains a function called doubler that just does one thing. It takes a variable called n as a parameter, it doubles the value of n, and then it returns that value. And then underneath this function, you can see that I'm defining a variable called x and assigning it a value. And then I'm calling the function twice, printing the results each time. Now I'm going to pretend to be a computer running this program. I'm going to put the current line number in this box, and I'm going to put the variables that I'm storing just underneath it. Okay, let's start. Line number 1 is a comment, so I'm going to ignore that. Line number 2 is blank, so that's easy. And line number 3 is the function definition for doubler, so I'm going to skip past that, but I'm going to remember that if I ever need to call doubler, then I'll go back to line 3. Okay, line 4, 5, 6, 7, those are all part of the doubler function. Line 8, some actual code. So I'm going to make a variable called x and store 100 in it. Okay, line 9, so I need to print something. But first, I've got to run the doubler function. So we're going to go back to line 3, and I'm going to send it the value of x, which is 100. So I'll just write down 100, and I'm going to send that to my doubler function. So at this point, I come in, I'm the doubler function, and I'm running on line 3. And at the moment, I don't have any variables at all, but I'm taking a parameter. So here we go. Here comes my 100 that I've just received, and I'm going to store that locally as n. Now, if we move on to line 4, I need to double that and store it back into n. And then line 5, I'm going to return the value of n, which is now 200, back to the function that called me. And we're back. So I've just received this value of 200, which I'm going to print on the screen, and go on to the next line of code. So next line, I'm going to print whatever comes out of the doubler again, but I need to send it the value of x, which is still 100. So value of 100, here we go, send it to the doubler function. Hello, it's me again. Well, it's a different version of me. I've got no memory at all of what happened the last time. As you can see, I've got no variables stored at all, but I have just received this new parameter of 100. So I'm going to store that locally as n. And then on my next line of code, I'm going to double the value of n. And then I'm going to send whatever's in n now, which is 200, back where it came from. And now I've just received back the value of 200, which I'm going to print on the screen. And my program's done. So as you saw, whenever a program runs, it stores its variables, and it keeps track of what line of code it's on, and it keeps it all in a thing called the stack. Now that was quite a simple example. Let's have a look at a more complicated one.
Whether you're building dynamic network models or forecasting real-world behavior.
Okay, line 1, that's a comment. Line 2, that's blank. Line 3, a function called doubler, got it. Line 4, 5, 6, yeah, we'll skip those. Okay, let's start line 7. Line 14, we're going to print whatever comes out of the embiggen function when we send it a value of 100. Okay, 100. Okay, send it up. Right, so I'm the embiggen function starting on line 7, and I can see I've been sent the value of 100. So I'm going to go ahead and store that locally as x. Now notice that this x is not the same x as the one in the function that called me. This version of x only belongs to me. It only exists in this stack frame. So if I change this x, we won't have any effect on the X in the other stack frame. Okay, so in my line of code on line 8, I need to call the doubler function and send it, well, the value of 100. Okay, so let's send that up. And I'm the doubler function starting on line 3. Okay, so I've been sent the value of 100. I'm going to store that as n. And then I'm going to double n. And then I'm going to send the doubled value, which is 200, and send it back. There you go. Okay, thank you. So I've received the value of 200, which I'm going to store in my value of x. And now I need to send the contents of x, which is 200, back to the doubler function again. Okay, here we go. Thank you very much. I'm starting on line 3 and I've just received 200. Okay, so I'm going to store it as n and then double it. And then I'm going to send the new doubled value, 400, back down. And now I've received 400, so I'm going to store that in my x, and then I'm going to return it. Here we go. Oh, finally, I've been frozen for ages. Right, okay, I've now received 400, so I'm going to print that on the screen. And on my next line, line 15, I'm going to print x. Well, that's still 100, so x hasn't changed for me. I don't even know what's happened in all those other stack frames. So,
Okay, so you got the point, right? And every time you make a function call, there's a new call stack, and that's what we're saving the stack frame. The stack frame has local variables that we created within the function, including parameters, right? So I think this guy did a great job. Okay, so for storage binding, we're going to look at these 3 different type of bindings, depending where the variable will be allocated. So static and global variables relates to the ESS segment. Stack allocated variables, those refer to local variables created within a function. So they are allocated in the stack frame of the call stack frames, or in the call stack. And the heap allocated variables are for dynamic variables. So when you instantiate an object, for example, that instance variables, right, within that object, they are dynamically allocated because the object itself will be allocated in the heap. Okay, so variables that are bound to memory cells within the when the program begins execution, in the static and global, they remain in the same memory cell throughout the program execution. So of course, static and global variables, they have their pros and cons. So if the variables, those variables do not change, so they're actually constants, I think it's okay to create define them as static in a class, for example, or even static in functions, or global variables, where those are variables that you create outside any scope or within a, usually there's no such thing of any scope. You always have the scope, but usually the scope is the whole program file where you define those variables, right? Or the whole module. So I would say you have to be careful when using global variables. You guys already know, you did software engineering, you know the dangers of using global variables. But if it's a constant, there's a protection in place that will prevent you for misusing a global variable. So I use global variables when they are constants. Unfortunately, you can't create constants in Python, right? That's a problem. What I usually do, I use it's a naming convention to use all caps for constants. But I know that those are not actually constants, right? We can do that in Python. Here are some examples of X here, this code is in Python, so this is the global variable. It's going to be static allocated. And this is interesting. You guys know why I'm using global X here within the function?
That it uses the one on line 2.
Yeah, so if I didn't have line 5, what would be the problem? So let's say I remove line 5 and I had X plus equal 1. X is going to be a local variable, right? So in order for this function called function to explicitly say that I want to use X, but the global X, you have to prefix with global. Okay? So basically this is saying, look, don't create another X, right? Use the one that is already defined global. So this is what this global means. It's everybody knows.
Isn't it like in Python, if you don't have it defined inside there, but you have one outside, then it'll treat that variable on line 6 as the global one anyway?
No. You can test and to make sure this is correct, but if you don't use global, granted, this code here is doing plus equal, but you can try to do something like prints or you can try to do assign 5 to X, right? The X, you're not gonna be changing this X here. You're gonna be, Python will create a local X, will assign 5, and this X here will remain untouched. Because this X is the global. If you want to refer to this X here, you have to prefix with global, right? But we can test that some other time. Let's continue this on Thursday, okay? Finish now. We're going to do a practice on storage binding and scoping next time.